I'm out in my garage workshop now that I've finished that Hallicrafters SX71 restoration. What I would like to do is build up out here a workshop that is representative of a radio workshop after World War II, and I've arbitrarily decided before 1970. The reason that I chose 1970 is because I have a 1969 ICO catalog. Now, I have a number of other catalogs, but I arbitrarily chose 1970 because this catalog is a collection of the ICO equipment that was available as of 1969. So I'm going to arbitrarily use that as the cutoff date, in other words, before 1970. I considered a number of pieces of equipment. One thing that I would like to do is I'd like to have a capacitor tester that will test leakage. That night this Heath will as well. I'd also like to have a signal tracer, and I think you may have seen my videos on signal tracers and that kind of thing. And finally, I would like to have an RF signal generator. Now, I have several pieces of equipment by different manufacturers, but I have decided to restrict the workshop to ICO. So what I'm going to be doing is restoring where necessary, checking in every case, and building cables, doing anything else that needs to be done to build a small workshop, preferably right back there in that corner, using an ICO signal generator, an ICO capacitor tester, and the main criteria there is it has to be able to test leakage up to at least 400 volts. These are my own rules, by the way, and it has to include a signal tracer. Now, obviously, some other things are necessary. I'm going to include this variable auto transformer, and I'm also going to include a piece of modern equipment, the kilowatt, partly because it's a nice way to measure things like voltage and amperage and so on. Now, that particular one has a voltage dial on it, and it has a little ammeter in front, so I could do without this kilowatt, but I find it convenient. Now, there are some other things that I'll have to add to this bench. Obviously, some way of measuring voltage and some way of displaying signals, though an oscilloscope in a radio shop of the 1960s or 1950s would have been a little bit unusual. They tended to come into vogue during the 1960s and 70s with television. So, that's sort of where I'm going, and the first item that I think I'm going to work on is this signal generator made by ICO. And as I pick up each piece of equipment, I'll add on to this and show you in the catalog what it sold for back in 1969. Well, here's the entry from the catalog. As you can see, in 1969, this RF signal generator cost $32.95 in kit form and could be purchased wired for $44.95. I've brought it in to my inside shop, partly because it's a little warm this time of year in the garage. And so let's open this up and take a look at what sort of condition it's in. I've taken the chassis out of the cabinet, just removed the screws around the outside edge, and now I'm going to test the capacitors and the resistors in this unit. The resistors I'll just measure with an ohm meter. The capacitors I'll check with these two Peak Atlas meters. I'm not going to actually show you that process because I'm sure you've seen it 1,000 times before if you've watched these kinds of videos. And then I'll make a decision about which capacitors, if any, to replace, and that'll be in the next segment. Here is the unit in general. You might like to get a little bit of a look at how clean it is. I'm really surprised for an instrument of this age. The copper isn't even tarnished. So here is a test. Apologize for that glare. You see the capacitor is reading 13 nanofarads, or microfarads, I'm sorry. 13 microfarads with an ESR of 0.7 ohms. This is the electrolytic capacitor that's in the unit. You see it right there, and the leads come here and there, and that's close enough for as far as I'm concerned to the value, and the ESR is low enough, so I'm going to leave that capacitor in for now. And I've checked the other capacitors, and except for the ones across the AC line, which I may change out for safety capacitors, I have not found any that are out of spec too far. So for example, these 400 volt units, I checked the leakage on them, and at 400 volts the leakage is within reason. It's a milliamp or a few microamps. So I'm basically going to change a little of my philosophy on these things. I used to just replace all capacitors out of hand in vintage equipment on the theory that if they're not bad now, they will be someday. But I've changed my mind on that, and in fact what I think I'm going to do is try to find a way to put a fuse in the AC line to protect the power transformer in case that any capacitors ever do short, and try to go with as much of the original as possible. So at this point, I think the next step is a power up on the unit to see whether it will operate. Before I did the power up, I thought it might be a good idea to check some resistance readings. Now, I checked the resistors themselves earlier, but all of them seem to be within reason of where they're supposed to be. Generally, resistors, these old carbon resistors, tend to go up in value. So if you measure across them and you get a value close to what's on the schematic, you usually can go with that, at least until you have some indication of a problem. But one of the things that I noticed is that the rectifier, which is the little unit that's right in there, point to it. It's a little unusual. It's this unit right here. Measures 5 meg in one direction and 2 meg in the other direction. So I think we can safely assume that this rectifier is bad. So what I've done is I've disconnected the wire from that, partly so I could do a measurement without the circuit getting in the way. And so now what I'm going to do is, before I power it up, I'm going to try putting a diode, a silicon diode, in place of that rectifier. The rectifier is clearly bad, so let's replace that first before we try to do a power up. Okay, before I power this up, what I've done is I've jumpered in a 1N4004 diode. The last digit, in case you're unaware of these markings, the 4004 basically is a 400 PIV diode. PIV stands for peak inverse voltage. A good rule of thumb is to use a PIV rating at least twice as high as the AC supplying a power supply. In this case, the AC is 110, so that would mean use a PIV of at least 220. A 4002 is a 200 PIV diode, so I decided to go with a 4004, which is almost twice the PIV needed in this circuit. Before I also go any further on this, I need to point out that if you do not understand safety, if you do not have sufficient training in electronics and safe practices, don't try this. YouTube videos are not a good way to learn for a beginner. Best way for a beginner is get a mentor, someone who understands and has years of experience at this, who can help guide you along. Sometimes you can find those at amateur radio clubs, sometimes at a local vocational school, or maybe just someone who used to work on TVs or something of that sort, but someone who has some experience who can help you. Don't try this on your own, assuming that, well, gee, I watched a YouTube video, so I know what I'm doing. If you also haven't seen the video I did on the depth difference, I would suggest you look at that one. This is an isolation transformer, and it's very important that you always use isolation transformers when working on AC equipment. And anything that you plug into the AC line, whether it's a piece of equipment you're going to work on, or it's the test leads of your meter, etc., requires that you know what you're doing and that the meter and other things be appropriately rated. I'm not going to go into those things here because this is not intended to be for a video for pure beginners, at least not to instruct you on how to do this work. You're certainly free to watch it for entertainment value, but do not assume that because you've seen this video that you know how to work on electronic equipment. Pardon the schoolmarm style, but it really is important. I don't want people getting killed because they saw one of my videos and thought, well, gee, I know how to fix this stuff now, and they really haven't learned the safety rules. Well, okay, so I've plugged that in, or jumpered that diode in place of the bad rectifier that was in the circuit. So now what I'm going to do is turn up the voltage here to about 90 or so volts, and I'm going to check the voltage out of the power supply, and you notice it's reading 146 volts, 145. Now as the tubes warm up, they'll draw current and this will drop. What I want to see is how high it goes. The reason is, with just 90 volts in, I got 130 volts out. And why am I doing this? Well, especially in older equipment, when you replace the rectifiers, they often were very inefficient in the day. And therefore, if you use a modern silicon diode, like the one that I'm using here, this 4004, maybe a little hard to see. Let me zero in a little better on that. You can see the little diode there. They're much more efficient. That means that your voltage is much higher. So I think what I'm going to do in this case is I'm going to put a series resistor with that diode so that it drops the DC voltage a little bit. I hope you understand what I'm saying here. I'm just basically making this diode as inefficient as the old diodes of the day by putting a resistor in series. So let me see if I can figure out what size resistor to use, and I'll be back in a little bit. A quick aside, I thought, since I'm working on a vintage piece of equipment there, that to try to determine the correct resistor value, it would be appropriate for me to get out this vintage resistance substitution box. It's also made by ICO. I assembled this, gosh, I guess in the late 50s, certainly no later than about 1960, from an ICO kit. It basically just provides a series of resistors in steps, and I put that in series with the diode. Let me show you the schematic, get an idea. You see there is the diode CR1, and so I have inserted a resistor in series with that. And what I've determined is that about 680 ohms is about right to reduce the voltage at that junction to 125 volts, which is the voltage that is specified for the day. Now you don't want that to go much above 150 volts, because that's what these capacitors are rated for, is 150. So I'm going to put a 680 ohm resistor in series with CR1 and then see how this how this power supply works. Okay, now the voltage that's supposed to read 110 volts is reading 108.3, which I think is close enough for what I'm looking for here. We probably will have to reset the calibration on this unit anyway. So I think we're good to go. Now I'm going to check out the functions. I've been checking the dial calibration. I'm up to band E, which is the most critical in terms of stray capacitance and so on. And I hope you can see that I have the dial set right at 20 megahertz. Looks like it's not going to focus any closer there. 20 megahertz. And now let's go up here and take a look at the counter on the oscilloscope. And it's reading 20.004, 20.005, which is very, very accurate for an instrument of this age. So I have checked the calibration, the mid-band calibration of all of these bands, as well as the end-to-end from band A through band E. And I point out that band F is actually not really a band, it's really just a harmonic of band E. So if band E is calibrated, well, the harmonics on band F will also be correct. I will also point out that in a generator of this age, or of this design actually, let me show you, there are only these inductors to adjust. There are no padders in this instrument. So basically it's the stray capacitance and the wiring and so on, and the tracking of the variable capacitor that determines how accurate the band edges are. This instrument is pretty accurate, except at the very, very top end of band B it reads a little bit low, and at the very, very bottom of band A it reads a little bit high. In other words, if you set the oscillator to the center frequency, to the middle of the band, they tend to move a little bit. Well, there's really no way without adding some pattern capacitors that we could fix that. So I don't want to change the design of the instrument. At any rate, I'm at a point now where I'm satisfied that this signal generator works. It puts out frequencies all the way up to the upper limit, which is actually 145 megahertz. But you can only get megahertz on band F1. The basic top of the instrument is 37 megahertz. So at any rate, I'm happy with the dial calibration. The changes that I made to the circuit to fix that selenium rectifier appear to be working okay. So I think I'm ready to button this up, put it back on the workbench, and be ready to move on to the next piece of equipment. However, because it may be some time before I can get to the next piece of equipment on the workbench, what I'm going to do is wrap up this video at this point. Hope that you have enjoyed it so far, and that you'll stay tuned for a future video in this series as I add more instruments to my vintage workbench. In the meantime, have a nice day.